Okay, so for the last talk of this session, we have Jesse Sigal who's going to talk about Paella, algebraic effects with parameters and their handlers. Please.
Thanks. Hi, I'm Jesse. This is joint work with Ohad, Kammar, Cristina, Matache, and Conor McBride. This is currently work in progress, implemented in Idris 2. There'll be a link at the end so you can look at the repo if you want. And also, just to begin with, this parameters here is completely different from what Wilmer was talking about, just FYI. So here's a quick overview. First, I'm going to talk about normal algebraic effects and handlers and how you can implement them with computation trees. Then I'm going to go over a example program using R setup and explain how that relates to Kripke computation trees, and then I'm going to conclude. So algebraic effects and handlers. So why do we like to use them? Well, it's a great way of adding user-defined effects to a programming language, and they're also quite nicely mathematically structured, so that aids in reasoning and other things. Lots of examples of algebraic effects and handlers. You have backtracking, non-deterministic choice, global state, exceptions, yielding, concurrency, many different things. And one way to implement them is you can have programs be computation trees. So especially if you're implementing it as a library in, say, Haskell or Idris, you can implement them as computation trees. And then programs are exactly computation trees. And handlers for them are just folds over the trees. So let's look at an example computation tree. Oh, that's a bit later, actually. First, let's introduce the effects that the tree is going to use. So here we have some collections, some effects that we might use for state. So I've divided them up into two different classes. First, we have static or global state. So here we have a collection of locations, and each of the locations is going to hold a bit. So we have two operations, read and write. Read takes location, gives a bit. Write takes location, a bit, and sets the location to the bit. And these are good for global state. But what happens if we want dynamic state or local state? So we can have one operation called new, which takes a bit for our new location and returns the fresh location. And we also could, for example, have GC for garbage collection, which takes a garbage collection policy and does some magic behind the scenes that changes the shape of the heap. So these two things, these two classes are sort of different from each other. If we want to support new and GC, the location type needs to be abstract or dynamic. And specifically what I mean by this is we want to avoid creating counterfeit locations. So we don't want to materialize location, say like if your pointers are just integers and your type system doesn't help you. If you materialize a location which you didn't get from new, then you could reference memory that is unallocated or as garbage or whatever. So we want to avoid that. And also, if you do garbage collection, that could rearrange the place or rearrange your memory. And so you want to make sure that you're still talking about the same place in memory that you thought you were. And so you want to be able to respect changes in memory location. So we have an example below here. So what happens if you capture a reference inside a closure? So the first thing we do is allocate a new reference initialized to the 1 bit. Then we define a continuation, which captures the newly defined location in its body. So we've closed over it. Next, we do something with the GC behind the scenes. So say we compact everything, get rid of some space, and rearrange the shape of the heap. And now we call our continuation. So depending on how we implemented this, we might end up with a dangling pointer. We might be talking about a location which has been taken away by the GC. So we want to avoid that. So before we talk about how we solve this, let's look at ordinary computation trees. So here I have an example using global state. That's what the GS stands for. So we're going to perform a few operations. The data type of locations here is just two locations, location A and location B, and bits are just 0 and 1. So we have a little program here on the left-hand side and a computation tree which this program represents. And the first thing that we do is going to read from location A and bind it to variable A, then do the same for location B. Then we're going to write the value bound in the variable B to location A, and vice versa for location B and the value A. And then we're just going to return what's currently in location A and currently in location B, which corresponds to just the variable B and the variable A. So the computation tree, which corresponds to this, is on the right-hand side. So the very first thing we do is we're always going to read from location A no matter what. And there's two things that we could read from location A. We could either read a 1 or a 0, and that corresponds in the program to the variable little a. The next thing that we're going to do, no matter what, is we're always going to read from location B. And reading from location B, again, has two different options. We either get a 1 or a 0, and that corresponds to the variable little b. And again, the next thing we're going to do, no matter what, is write. But here we have some different things that which we might write. So here, we're going to write to location A, which is the third line of the program here. But what are we going to write to A? We're going to write whatever came from little b. So if we trace our way through the path of the tree, we read a 1 from A, and we read a 1 from B. So we're going to write a 1 from A. And here we read a 0 from B, so now we're going to write a 0 to A. And similarly for the second half of the tree. And again, if we go back to the top, now we're in the 4th line of the program here. We're going to write a value to location B. And we trace our way through the tree. So we see we got to this node up here by reading a 1 from A. And so now we write a 1 to B. And similarly for the rest of the tree. And then the leaves are just returning the values down here. So this computation tree came from the program here. And actually, this monad that I defined up here, free, that's actually going to be implemented in terms of computation trees. So it's just a normal tree monad, and it has the normal tree monad structure, where return is just making a leaf, and the bind is just grafting trees together. So how do we actually get access to these operations read and write? Well, we're going to define an algebraic signature. So here I've defined an algebraic signature op.gs, consists of 2 operations, read and write, which are just data types. And we see here that we said that read goes from location to bits, and write goes from locations paired with bits to unit. OK, so that's normal computation trees. Here's the data type. So the first thing that we have is the data type for algebraic operation signatures. And then an index type, which takes a whole bunch of algebraic operation signatures, gives a full algebraic signature. So we can see here that was an example. And now we have our monad, which is the tree data type. So this tree data type has 2 constructors. We can use the return constructor, which just makes a leaf. So we can see here that return takes an x and gives us a tree which has leaves of type x. And then the more interesting case is op, which will allow us to use subtrees. So the first thing that we do is we get something from our signature. So this is going to be a specific operation, for example, read or write. And then we're going to pair some value, which is the argument of the signature. So for example, for read, this would be a location. And then we have a function which goes from arity to trees which also have leaves of x. So for example, for read, this is a bit. And so now we can see here how this gives us our subtrees. So if this is a bit here, then it's a function which takes a bit. So we can evaluate it twice and get the 2 different subtrees. And then all this information together gives us a tree. So this is how we get a branching factor. OK, so now we've seen algebraic effects and handlers. How are we going to make parameterized algebraic effects and handlers? So here I've highlighted the things that we're going to change. So here we have some types involved, and we're going to change these. And we also have some function arrows, both on like the top level and inside the product here. And then we also have some products. So in order to make this parameterized, we're going to change these to families. And so by family, which I'll talk about later, it's a index type. And not only are we going to change some of these types to index types, we're going to change the arrows to maps between index families, index types. And we're also going to change our definition of product. And then we also have this other exponential function type thing here as well. So that's what we're going to show. Before we do that, let's see what we can actually do with parameterized algebraic effects and handlers. So this example is basically inspired by type checking a dependently typed program using elaboration and unification. So I'll get more into that as I go through the operations. So specifically, we have some clocks which can tick upwards and have work done to them. And we also have some tasks, which is going to be cooperative threading. And we're going to define a signature here. So we have a whole bunch of operations. The first one is going to be new. That's going to allocate a fresh clock initialized with some natural number. And then that's going to give us back a fresh clock. And this represents a unification variable. We can synchronize 2 clocks by adding their ticks together. So a clock is going to hold a natural number of ticks, and here we can unify them. So not only are we going to add these 2 together, but from this point onwards, the 2 things that we synced are now going to go in lockstep in the future. So if I have a clock 1 here and a clock 2 here, and I synchronize them together, then they're always going to read the same in the future as well. We can also tick a clock forward. So here, work ticks a clock and a number of steps which are going to tick it forward. It's going to tick it that number of steps forward. And then we can also wait on a clock. So wait until says, given a clock, wait until it's at least this value. It might not be woken up, or we might not stop waiting at exactly that value, but we might be woken up sometime in the future. And then we have 3 operations for threading. So we can stop, presumably in a child thread. We can fork, which is either going to give us the task ID or just a unit if we're the child. And we can also wait on a task for it to finish. So let's look at a program which uses these operations. So here we have a program. So first of all, I'm just going to point out that due to some things I'll talk about at the very end, we have to have some explicit let binding. So that's what this column on the right-hand side is. We just have some explicit let binding that we have to do, but that's all that that is. So in the program itself, what are we going to do? Well, we're going to allocate 3 new clocks, C1, C2, and C3, initialized to 0, 1, and 3. Then we're going to do some work on clocks C1 and C2, increasing C1 by 50 and C2 by 60. And now we're going to fork. So in the child thread is going to wait until the clock C3 is 40. Note that C3 was initialized to 3, so it's nowhere near 40 to begin with. And then after we wait until C3 is at least 40, then we can do some more work on C1. In the parent thread, what we're going to do is we're going to sync C1 and C3. So C1 was 50 starting at 0, so it's currently 50. So when we sync C1 and C3, that's going to push C3 to the value of 50, which means that the child thread is now unblocked, so the child thread can do work. And so now we're going to wait on the child thread, so the child thread will eventually have some work done, and then we'll have finished waiting for it, and then we can sync clock C1 and C2. And so this is supposed to elicit the idea of having unification variables that can have work done to them during the process of elaboration. And you might have different parts of your program which update your unification variables and give them more information. And you want to make sure that you don't get stuck on them falsely. And so you want to, for example, wait until some more information has been added to the context for that. So here we have time-aware continuations. So each of the continuations, everything after the binds, are our first-class functions. There are continuations. And they're going to be updated every time we do some work and sync the clocks, and also when we create a new task. And so these are our hidden parameters, which we're going to talk about soon. And the library itself makes sure that all the continuations are updated with the new information. So what's the takeaway? So a clock has a dynamic value, which is based on the world. And in this case, the world are clocks and tasks. Each new and fork changes the world. And we can solve this by just glomming together enough state, but it's not really nice. And you'd also need an extra level of indirection for your I/O references, because when we synchronize 2 clocks, they need to be the same in the future. So we need to tell 2 clocks to now point to the same location. And clocks and tasks here are example of parameters, where parameters here means parameterized algebraic theories from Sam Staton. Another example of parameters is, say we're dealing with local state, so we have heap allocated values, then the parameter for local state is going to be the shape of the heap. And so here we introduce Paella, a parameterized algebraic effect for library languages. And the idea is to do the same thing that we did with normal algebraic effects and handlers with computation trees, but we're going to use world-aware types, i.e. Kripke semantics. So let's talk about Kripke computation trees. So the first thing that we have to define is some world. So here I haven't defined an explicit world, but depending on exactly what you're doing, for example, local state or our clocks and tasks thing, this type of world is going to be different. And this type of world needs to support some operations, so we need to be able to talk about going between worlds. So we have this squiggle arrow here, which tells us how to go from a source to a target world. We need to be able to go from a world to itself using an identity, and we need to compose them. So world needs to be a category. And this is going to give us our ability to move between worlds. Now that we have worlds, we can talk about families. So here we can see a family takes a world and gives back a type. So basically, depending on what world we're in, something that's a family can change. It can have different valid values based on what world we're in. And we also have a notion of map between families. So here we have another arrow type. If we want to go from family F to family G, then what we say is, give me a world W, and then provide a way from going to F in world W to G in world W. And we also have an identity for families. So at every world W, it's just the identity map. And we also have a way to compose maps between families, which basically says if we want to do beta after alpha at world W, then just do alpha in world W and follow it by beta in world W. So again, we have a categorical structure here. So that's families. So now we can look at the core types again. So now our operation signature, before args and arity were just types, like locations and bits, but now they're a family. So depending on the world we're in, we're going to have something that depends on the world. And signature is basically the same. And now we can look at our tree data type again. So we still have two ways of forming trees. We can form leaves using return, and we can combine subtrees using op. So here we've replaced our normal arrow with a map between families, and I've expanded the type off to the side. So as a normal type, this says, given a world W and something FW, then form a tree. So now what this is saying is that instead of just having a single value at our leaves, we have a world W at our leaf and some value of F in that world. Now we also have our way of combining subtrees, and we're going to use some notion of product of families, and we're going to also use some notion of exponentials of families. So if we just stare at this type now, this is a similar type as we had before, and just ignore the new products and exponentials for now, because we're going to talk about that in a sec. But we can see here that really what we've done is just literally exactly the same thing. We've just changed our basic domain of discourse to families instead of types. So what we also want to do is we also want to be able to update our computations to work in a future world. And so we're going to add actions to our families. So this is also known as pre-sheaves. So what's an action over family F? Well, it says if we have two worlds W and W prime, and we have a way to go from world W to world W prime with row, then we want a way to take values of F in world W to values of F in world W prime. So that's what an action is. But the way that we actually implement this in Idris code is we're not going to use action over directly. We're going to use a different approach by Alay et al. And Fiore and Shamovantchev using box coalgebras. So what's a box coalgebra? The first thing we need to do is define a type box, which takes a family F and gives us back another family. So what is box F at world W? Box F at world W is a family when given world W prime. It asks for a map from W to W prime and gives us back something of family F in world W prime. So how are we going to use this box? Well, we're going to use it in the following data type. So this data type here, for specific family F, we're going to ask for a map next, which goes from F to box F as a family map. So if I expand this type here out, as I did in the line below, we see it asks for a world W, because we're using a map between families. And then it's going to ask for something of F in world W, a new world W prime, a way to get from W to W prime, and it's going to return something of type F in W prime. So if we just stare at this type signature down here and this type signature up there, we can see it's exactly the same. We've just swapped some things around. So this map next contains exactly the same information as an action over. And indeed, if we have a box coalgebra, then we can just use this other function map here to get an action over. And the reason why we do it this way is it sort of lets us separate out the definition of families from their action. And so it's sort of a nice implementation detail which lets you define things modularly. It's not strictly necessary, but it's a nice thing to do. So let's look at some basic families. So the most basic family, I think, is just the constant family. So no matter what world we're in, we're going to always just be constantly a type T. So the box coalgebra structure here, you can see I'm ignoring basically everything and just always returning the same thing. So we capture that intuitively here. Next, we have env, which basically says take something in the environment of world W. So this is just going to be a representable function, if you know what that is. And so we just have a map out of W. And what's the box coalgebra structure here? Well, so if we have something in environment W0, that basically means we have a map that goes from W0 to W. And if we have something in world W, which is what this row is, and we want to bring this row into some future world W prime, and we have a map row prime, which gets us from W to the future world W prime, then the only thing we need to do is just compose row and row prime. And we're going to use this as env later. So what about products of families with actions? So first, we need an auxiliary data type for all. So that's going to take a SNOC list, which is just a list that grows on the right instead of the left. It's going to have elements of type A. And we're going to have some predicate, which takes something of type A and gives a type. And then we have the type of for all. So we can either have an empty for all. So lin is just nil backwards because people are funny. And next, we have cons on the back. So if we have a list of SX's, all which satisfy P, and we have another X which satisfies P, then we can just put X on the back, and we still have a collection of things which all satisfy P. So how can we use this to take a product of families? So if we have a SNOC list of families, so a list of families, we can create a new family. And what is this new family at world W? Well, it just says, for all the families that we have, just evaluate each family at world W. So a product of families is just something from each of them, all evaluated at the same world. And also, I haven't written the definition, but we also have an action structure, a box coalgebra structure for the family, for the product of all the families, if each of the families themselves has a box coalgebra structure. So this is just a pointwise combination of all the families. Now, for the most interesting bit, we have the exponentials of families with actions. So before, when we defined this arrow type here, that was a map between families. But now we want a map between families with actions. And so not only that, we want to turn that into a family itself. So here, if I have F and G, which are families, and I want to make a new family, which is the maps between F and G, we define it as below. So a map from F to G in world W is just a map of families, but it's not a map of families from F to G. We also add M of W here. So I've expanded this type here in this comment down below. So if we have this exponential in world W, this thing on the right-hand side says, given a future world W prime and a way to get from W to W prime, then I can promote this function from F to G intuitively from world W to world W prime. And this is what's going to allow us to promote our continuations into a future world. So this exponential behaves like a normal exponential. So if we have an F and a G, or if we have a function which goes from F to G and an F, then we can just evaluate it and get something at G. And we can also do currying and other stuff like that. So it behaves like an exponential like it should. And it also has an action structure. So in world W, if we have an alpha, which intuitively goes from F to G, and we want to evaluate this alpha in some future world W prime, and we have a row which gets us from W to W prime, then intuitively what we're going to do is we're going to take this row and we're going to remember it and save it for later. And every time in the future world W prime that we use this alpha, we're just going to prepend this row. So we're going to remember how we got there in the future. And so this is what lets us, again, update our continuations to work in the future. So here's the core types, the trees that I showed. So I'm not going to put the definitions up here, but these trees also have an action. They also have a folding operation, just like our other trees did. And these also have a monad structure in a suitable sense. So it has enough support for effects and handlers and making monadic programs. But now that we explained what this famprod is and what this exponential is, let's expand this type out into a normal type. So here I've inlined all the abstractions which I just defined, starting from this bottom line here. So looking at this bottom line here, if I expand everything out, it says take a world and take something of the operations arguments in this world, and then let's look at how we branch for the subtrees. So the branching of the subtrees, instead of just having arity, we now have two different other things which we can branch on. We can branch on a future world W prime. So for each future world W prime, we have to provide a subtree. And for each way of getting from W to this future world W prime, we also need to branch. And then we also branch on whatever the arity of the operation is, but in the future world W prime. And then we also ask for our tree to exist in the future world W prime. And so basically what this is saying is that each of our continuations, each of the things that we have on the right side of the monadic bind, need to support any possible future world W prime and any possible way that we got there. And so these extra arguments here, which are hidden under the abstractions, allow the continuations to be updated and run in any future world. So let's conclude. So we defined a type of worlds and families over such worlds. We defined families with actions, also known as presheaves, as well as their products and exponentials. We defined a new computation tree whose branching supports any future world. And these trees also have an action and folding operation, and they also form monads, so we can create computations which are updatable. So some future prospects. We want to, and already have a little bit, implemented full ground local state as an effect and handler. So that means you have ground values like integers and booleans, but you also have pointers, so you can do things like linked lists. And we want to implement the Tarjan-Slater transform. So the Tarjan-Slater transform takes a mutable data structure and creates a partially or fully static data structure, meaning, for example, if you have a linked list, which is normally mutable, say, for example, you want to look at all the possible histories under updates of this mutable linked list, that's what the Tarjan-Slater transform does for you automatically. It creates a new data type, which has the same operations as a linked list, but it also keeps around the previous versions. And it doesn't do this just by copying things around. It does it in a much better way with sharing and whatnot. We also want to do elaboration and constraint solving with metavariables. This is what I was talking about in the example before. And there's already some work in progress, which Conor has done in Haskell. And we also want to do some more complicated threading examples, which is also work in progress in Idris 2. We also want to do some improved ergonomics. So you saw how we have to do explicit let binding. And that's sort of just because we can't use the normal do notation because we have an extra argument floating around, which is the worlds. So there's two ways that we can fix this. One way is semantic reflection in Idris 2, which is basically using Idris 2 syntax as a DSL inside Idris 2. So you use some fun little bracket things, sort of like template Haskell, and that turns that into an Idris AST, and you can write a consumer of the Idris AST. So semantic reflection would allow us to use Idris 2's variable binding, which is already built in, and then we can just transform a program written in normal Idris 2 syntax into our thing. Also, there's some horrible, horrible hacky things you can do in Haskell with type classes and local instances and unsafe, coerced sort of things, and that gets rid of the extra argument and makes the constraint solver solve it for you. You can see the repo by following the QR code or the link. I emphasize it's work in progress. The code is documented, but it could probably do with a little bit more documentation. But yeah, thanks for listening.
Thank you. Do you have questions? Max?
Just to this last part about improved ergonomics, could you go back to the example and show us which part would go away?
Everything on the right-hand side column.
Okay, great.
Yeah, so you just use normal do syntax. So, I mean, because, yeah, so.
Okay, I think that's what I hoped the answer was.
Other questions? I've got one, which is about, do you think it will be possible to prove equivalence of programs in this setting by relating the two computation trees, like, I don't know, trying to build some kind of bi-simulations?
We're not focused on that.
Okay.
Yeah, we're using Idris 2 as a dependently typed programming language, not as any way of doing formal reasoning. So for example, when I defined what a presheaf is, you'll notice I didn't talk about the presheaf laws. So we just expect the user to write the correct thing. But maybe in the future, we'll do some reasoning things, but not at the moment.
Okay, thanks.
Thanks.
Other questions? Well, otherwise can stop here. Oh, one question? Okay, please.
What's your ambition for the library? Where will this go?
So it'll be a library in Idris 2, and maybe also Haskell. And yes, we want to use it to do cool things like the Tarjan-Slater transform, basically something which would be incredibly fiddly to do by hand, but gives you a lot of benefit. So I think we mostly want to use this to explore the benefits you can get with parameterized algebraic theories. Specifically, Conor McBride had a pre-existing problem implementing type checkers for dependently typed programming languages, specifically with the metavariables and things not being updated properly. And they were saying, I don't know if it was for epigram or for some other stuff, they had to explicitly take continuations and turn them into a data structure in order to make sure that you could update all the metavariables in the closure, and they absolutely hated that. So that's one motivation among the other ones.